Hey, Charles.
Hey, Pete.
Hey, want to learn about some overloads?
Absolutely.
Oh, yeah. Well, overloads are fun. This phenomena occurs when you're measuring some sort of signal from, could be an accelerometer, a strain gauge, pressure transducer, whatever it is, and that outputs a voltage. And the voltage that you're measuring, if it exceeds the range of the transducer or the measurement system, what the voltage it's capable of measuring, you get some interesting problems. That's called a overload.
Okay.
I'll show you a small example here. With this signal is not overload. Every signal in the world is composed of sine waves. The Fourier transform says that. So I got a sine wave showing here, and you can see it looks nice and sinusoidal, and we see a nice single frequency over here. And part of the reason I'm able to measure this successfully is because it fits within the maximum input voltage of my SCADIS. Normally a SCADIS can measure up to 10 volts input, but you can set the range on the channel to be lower. For example, in this case it's actually 1 volt. So the maximum level here is 1 volt, and you can see the signal is below that. But if you increase the voltage of your signal above 1 volt, you got some problems, Charles. Instead of a nice sine wave, what does this sucker look like?
Looks like a square wave or something.
Yeah, and when you get a square wave, Fourier transform, there's harmonics that are
Yep.
produced to create the square wave. So you start to get some distortion in the signal, and it's not right. You're not getting the right peaks, etc. So that's an overload condition, which I guess really what we're talking about here is trying to avoid overloads if possible. So square wave produces these weird harmonics. That's one kind of distortion that an overload can create. Would you like to see that in real life?
Yeah. I love demos.
Okay. Well, so I got a signal generator here, Charles, and actually I got a BNCT here that outputs the same voltage, splits it out, and it's going into this SCADIS here into channel 1 and channel 2. You can see
Okay.
the frequency spectrum of channel 1 here and the time domain of channel 1. And we got channel 2 here and the time domain of channel 2. Later in our discussion, I'll explain why I'm splitting it into 2. But for right now, we'll see the same thing in both channels. And we see a nice sine wave. Does that make sense so far?
Yep.
All right, I'm going to increase the voltage level of this signal. Ooh, it turned orange. I'm getting close to an overload. And if I keep going, oh, I'm in the red. I got an overload. You see how that's not quite looking like a sine wave anymore, Charles?
Yeah. Flat at the top. It's cut off.
Yeah, and if I keep going, that cutoff becomes more and more severe. Look at these harmonics.
Oh, yeah.
Yeah, so we get some nice harmonics. So that's that harmonic distortion I was talking about due to an overload. Nice, huh?
Yeah. I want to avoid that.
All right. Well, so just kind of recap, no overload, linear scale. I got a nice single sine wave. When I get an overload in this linear scale, I can start to see some distortion,
hmm
harmonic distortion, I guess. And that's because it's being clipped in the time domain, get the square wave effect, which produces those harmonics. Now, if we go a little bit further, if I was to look at this in the log scale, even though it looks like a single frequency here, log kind of shows the low amplitude frequencies a bit more.
hmm
You can see there's actually multiples of that signal. This signal generator is probably, not the highest quality, so it's actually outputting some harmonics of the main signal.
Right.
When we have an overload on it and we look at it in the log scale, look, there's even more distortions or more harmonics. Do you see that?
Yeah.
Yeah. And something else. You see the level of the noise background here?
It's higher than the overloaded one.
Yeah, it is. So the noise floor is raised or higher as well, which you couldn't really see before. We just saw the harmonics when we were looking on the linear scale, but in fact it's a bit higher. Want to see that?
Yeah.
All right. You asked for it, you'll get it here. So maybe I'll lower this amplitude back down. Now I'm not overloading. Notice it latches to show me that there was an overload at one point. I can clear it by, you can actually double click here, it clears it. And we'll look at this signal in the log scale. And yeah, we see with the signal generator, it does have some harmonics, but we're not overloaded yet. So let's see what happens if that changes when I overload it. Increasing here, got a lot of square. Did you see that noise floor come up?
Oh yeah, it raised right up.
Yeah, it's like magic. You get, almost no noise and just some nice looking harmonics. But when you have that overload, tons of harmonics and a big increase in the noise floor. So that's something, huh?
Yeah.
Yeah. So really there's kind of two effects from the overload here. There's harmonics, and because of the sharp transitions in the signal created by the clipping, we get a broadband frequency effect that goes over all the frequency range. So how do we get into these overload situations? Well, one way is if your transducer is outputting more than 10 volts and you're trying to measure it with a SCADIS that only can record up to 10 volts. But another reason, and a little more common, is we get into these gain and quantization issues. If we look at this signal here, is anything weird about it, Charles?
Yeah, it looks a bit blurry, as it says, or fuzzy. I might need my glasses. Prescription updated.
It's kind of like if you zoom in, it looks a little like there's discrete intervals or values there. It's maybe another word would be stair-steppy. And that's because we don't have enough data points or bits, digital pieces of information along the Y scale to digitize it properly. You see there's a little gray signal here.
Mm-hmm.
So that might be the actual voltage signal coming out of our transducer. But if we don't have enough bits along the Y scale, we're going to see this stair-step effect instead. So like you see in the red signal, because the signal can only be digitized at these values. That's called quantization error, which we don't really want. Today's measurement systems, they're 24-bit. So that means if you take 2 to the 24th, this is the number of data points along the y-axis that we can digitize with. There's like 16 million data points. That's a lot of data points, huh?
That's a lot of data points.
Yeah, so you'd think you're all set, but let's take, now I'm going to switch things up. I'm going to give you a 12-bit example. But again, SCADIS is 24 bits. 12 bits means we have 2 to the 12th data points, or 4,096 data points we could put along the y-axis. And the only reason I did this is I'm not very good at math with 16 million. I could do 4096.
We forgive you.
And then, halfway down, 6 dB or half the voltage, 5 volts versus 10 volts, we have 2 to the 11th or 2048 data points, then 2 to the 10th, which is 1024, then 512. So as our signal level gets lower, guess what happens, Charles?
Less and less.
Yeah, less bits available
to
digitize. So you could have 16 million, but if your signal's low enough, you're going to run into a situation where like 0.01 volts or 0.0001 volts or whatever it is, even if the sine wave is at that amplitude, you could get the stair-step effect when it's really low, when it's way down here where there's very few bits left. Does that make sense to you?
That makes sense.
And so the solution is take that signal and gain it. So that means you take 0.01 volts, multiply it by 1,000. And if I multiply that by 1,000, what do I get?
10 volts.
10 volts. And so you amplify the signal by 1,000, you'll get 4,096 or whatever, 16 million bits, and you can digitize that signal super well along the y-axis. And of course, when we gain the signal up, the software is smart enough to divide by the gain so that you get the right voltage out. So we don't just gain it and leave it like that. We account for the gain.
That's good to know. Good to know. Good to know.
Yeah. But if our signal changed the level, like from 0.01 volts to 1 volt, for example.
Got a problem.
Yeah. You're taking that 1 volt, you're multiplying it by 1,000. You got 1,000 volts, but we can only measure 10 volts. So we'd have overload, clipping, and all those bad things.
Right.
This can happen sometimes. In the software, there's a feature called auto ranging that sets the gain levels. And if the levels are really small when you do this auto ranging, but then you go to do the measurement and they're really high, you could easily run into this overload. You got to be sure to auto range at the maximum level for the signals, whatever that is.
I see. Yeah, that
Yeah.
makes sense.
Yeah. Sometimes, the word range comes in. What's interesting about this, if I gain by 1,000, my input range is 10 volts, but effectively when I gain by 1,000, my input range is 0.01 volts. I really can't measure anything above 0.01 volts successfully because it would exceed 10 volts after it's amplified.
Yeah.
So, again, you got a very small signal and you set the signal range to 10 volts, you might run into some quantization error. If you gain it up and you have a range that's really small as a result of doing a gain, then you got clipping and overloading. So we could have underload situations, overload situations. Underload might look like this. You got a little bit of fuzziness, so to speak, on the data. There are bars in the software that kind of indicate the level relative to the range. And if you see a white bar like this, it means the signal's not using much of the range, which might be normal if you have no vibration going on. It'd be measuring 0. But if you expect that there's a decent amount of vibration, you wouldn't want to see something like this. It means you're going to have poor dynamic range. It's hard to measure. You got quantization problems. What we want to do is optimize the input range, i.e. the gain, on your acquisition system to kind of match the signal. So if I amplify this up, I could have a nice, beautiful sine wave.
Exactly.
And have a large dynamic range, and the bar will turn green, say everything's good. Make sense?
Yeah.
If we gained it up too much and we exceeded the level with whatever the signal is, we'd have some clipping in the time domain, we'd have harmonic distortion, we'd get the red overload.
Yeah, can't overdo it.
Yeah, and we got some other colors like orange. So what's interesting, when we gain it up, we should probably leave ourselves a little bit of leeway. If I go and gain it up to exactly 10 volts, even if it increases a little bit, that's a overload, right?
Yep.
So you can define in the gaining process, the auto ranging process, something called headroom or overhead. And usually people use, I think by default, 6 dB in the software, but you can change it. 6 dB, if you remember from the other chart, if this was 10 volts, that's halfway down, that we're actually targeting 5 volts. Yeah. Our signal could double and we still wouldn't overload. And we get a decent number of bits. Half of 16 million, just 8 million bits.
I could live with that.
Yeah. So here's a mind stumper for you, because you'll hear this. Sometimes you could have signals with, different levels at different frequencies. You could even have some really high amplitude signals at very high frequency in the analog signal, which is outside the frequency range you're trying to measure, so outside your bandwidth or frequency range. Do you think that would be a problem if that was overload at that super high frequency? Would it matter if it's not within the band?
It's outside the bandwidth I'm looking at, right? So that should be fine, right?
Yeah, well, let's think about that a little bit more, or maybe even try it. So this is the scenario. We got, 10 volt input range, for example.
Yeah.
We got a signal, part of the signal in the lower frequencies is well within that range, so we should be able to digitize that. Then and this is our maximum frequency we can measure that we've set up for on the measurement system. We got this other signal, much higher, that's over the limit, right?
Yep.
And guess what? A SCADA system will say, that's overload. It's a problem. And
I want to change my answer.
Yeah, you change your answer. Maybe we could just actually try this. So I got an overload right now. I'm going to decrease the amplitude, get it back to normal. And again, just to show how you can clear these, I can say reset all here, double click here. And this is the reason I had 2 channels, Charles. I'm actually set them to measure 2 different bandwidths, The first channel is set to measure up to 25,000 hertz. The second channel is set to measure up to 6,000 hertz. And I'm going to slowly increase the frequency here. Oop, I'm going down. Better go up. And I'm going to go past where we can measure it with the second channel, past 6,400 hertz. I'll get out here, I don't know, 14,000 hertz. So you can see we got a signal out here, right?
Yeah.
And if I look at this in the time domain, you can see we still see amplitude in the time domain on the channel 1, which is sampling high, but we don't see any data on channel 2. So you'd think maybe it's ignoring it, for example. But let's increase the amplitude.
Okay.
If I go back to like the log, which shows stuff, notice both of these are showing an increased noise floor. If I take it back down so there's no overload, the noise floor on both channels is the same and pretty low. And then when I increase it, it goes high on both channels, even though in the time domain I seemingly can't measure the signal coming into channel 2 because I have a much lower bandwidth. This signal is entirely out there, but the SCADAS is flagging it as an overload, and it's a good thing it did because that noise floor is being severely affected, wouldn't you say?
I would say so, yeah.
And that's because when we talk about overloads, and we have our SCADAS here, this is some of the stuff going on. We have an incoming analog signal. Then we convert that analog signal to digital with an ADC, and then we got our digitized signal. And we have some filters in there and stuff. But this incoming analog signal, if it's 20 volts and it's exceeding the threshold of 10 volts, it's clipping in the analog sense. And that actually passes through as a overload. So we check, because we want to know when we digitize this, we're actually digitizing the proper signal, not a clipped analog signal. Does that kind of make sense to you?
Yeah, that does make sense.
Yeah, so even though it's not something that we'll see when we look at the digital output, because we're maybe looking at a lower bandwidth, it's definitely in the analog signal that gets digitized, and it causes the same problem. Doesn't matter if you have an overload in the digital domain or the analog domain, it's going to show the same problem. So in fact, the SCADAS is detecting or looking for overloads anywhere in this measurement chain so that one doesn't slip by and cause this distortion.
That's appreciated.
Yeah, that's a good thing, I think.
Yeah.
So maybe a little bit of practical stuff about Simcenter Testlab, how it handles overloads. We already saw the different lights and things like that, but I'll go back here. Okay, so we have no overload showing. I'm going to hit start on the measurement here, and it starts recording. And then while it's going, I'm going to create an overload by increasing the level, and then I'll turn it off. Notice, first of all, even though it was a momentary overload, it flagged it here. I'll hit stop. And then it comes up and actually says, hey, you got some channels in overload, tells me the times here. I can say, yeah, I'll keep the run anyway. But yeah, if you were momentarily looking away when the overload happened, you're going to know when you look back at the screen because it clearly indicates it. And then later, if I give this data to someone else, and I'm looking in the navigator inside Testlab here, so I look at this run, notice there's a online overload logging. It actually kept track of those overloads, and that's part of the data information. I can pick view here and then double click on this, and it comes up and it's recorded for me where the overloads were. So if I wanted to, I could process the data before 5.97 seconds, know that it's without overloads. Pretty nice, huh, Charles?
That is pretty nice.
Yeah, I agree. So that's some additional ways that overloads are handled in Testlab. And maybe one more thing to point out, the transducers themselves could overload. In other words, a transducer can only output so much voltage itself, but it could experience vibration higher than that would create a higher output voltage than it's capable of. And this is one of the telltale signs of that. You see the accelerometer that's saturated here?
Yeah.
It has a lower peak than it should, which you wouldn't know if you're looking at it. But one of the telltale signs is it takes a while to recover. You see this slow sloping offset here?
Yeah.
That's an indication that the accelerometers themselves are overloading. So even if the data acquisition system can handle the voltage the Excel's outputting, like maybe the max it can output is 5 volts, but the vibration tries to make it output more than 5 volts because the vibration's very severe, whatever this
Mm-hmm.
big bump is.
Yep.
You can see this decay, and that's a telltale sign that something happened on the transducer side, creating an overload. The solution is to use a less sensitive accelerometer. So in this case, this is the 10 millivolt. It output less voltage for the same event, so it could be recorded, whereas this one that got saturated is the more sensitive 100 millivolts, so it's outputting more volts per G. So you got to tune the sensitivity of the accelerometer to the application to make sure the accelerometer itself doesn't kind of overload internally or saturate.
That makes sense.
All right. Well, thank you very much.